Good evening, everybody. My name is KETAN, and this is my presentation for my project Hardware Accelerator for Privacy Preserving CNN. First, let us take a look at the problem. So, we know that the AI models are growing in complexity and size, and the computation demands of every AI model are also increasing day by day. Hence, usually these models are not deployed on the local client devices such as mobile phones and laptops. These models mostly run on powerful cloud servers like Amazon Cloud Server or Google Cloud Server. So, if a consumer wants to use these models, they must first upload their data to these cloud servers. Then the AI ML model will perform the inference, analysis, and prediction based on the data, and it will return the result to the user. However, this raises a concern of privacy because if you want to perform analysis on sensitive user data like medical reports and government documents like passport, Aadhaar card, etc. So if you upload these sensitive documents to the cloud server where the AI ML model is deployed, then it is possible that attackers might be able to gain access to these documents by compromising the cloud server. So we know there are many attacks and hacking attempts on Google servers and Amazon servers. So if there is a backdoor or if the attacker can compromise the cloud server, he will be able to gain access to all the users, all the data that is being uploaded by the users. So this is a significant privacy concern. So how do we deal with this solution? Because we know AI ML models are crucial and they can only run on cloud servers, most of them. So we cannot get rid of that. So we try something called homomorphic encryption as one of the potential solutions. So what is homomorphic encryption? Homomorphic encryption is encrypting data in such a manner that it is valid to perform operations on the encrypted data. So what this means is that if I have a data and I encrypt it, the server can still perform operations directly on the encrypted data without decrypting it. And then after performing the operation, it can return the encrypted version of the result, and I can decrypt the result to get my actual computation result. So we can see an simple example here. Suppose the cloud server wants to perform a simple operation f of x is equal to x square. Now, traditionally, user will have to send 8.775. Suppose the user wants to calculate 8.775 whole square. So traditionally, the user will have to send 8.775 to the cloud server. The cloud server will compute x square, which is 77, and return the data. However, if an attacker compromises the cloud server, he can see that the user has sent 8.775. However, with homomorphic encryption, the user will first encrypt 8.775 using a secret key. After the data has been encrypted, it will be sent to the cloud server, which will perform regular X square on the encrypted data, and it will return another ciphertext to the user. As we can see, the A3, FH, MX, FT, EA, that is the encrypted form of the result. To decrypt this encrypted form, the user will again use the same secret key, and after that, he can obtain the decrypted result 77. So this is the concept of homomorphic encryption. We can see that the cloud server, at no point in time did the cloud server have access to the actual user data, 8.775. So even if an attacker is able to compromise the cloud server, he will only be able to see the encrypted version of the user data, and unless he has the secret key of the user, he will not be able to decrypt it. These schemes are quantum secure, which means even if you use the right parameters, we will discuss the parameters later on, but if you use the right parameters to encrypt, even quantum computers cannot brute force the scheme. Let us talk about some different types of homomorphic encryption schemes. So there's a lot of homomorphic encryption schemes. They all share the same property that it is valid to perform operations on encrypted form of the data. But the exact algorithms that they use to encrypt, decrypt, etc., they all differ based on the scheme. So the first scheme that was proposed was by Craig Gentry in his PhD thesis, a fully homomorphic encryption scheme. This was done in 2009. This was a POC. It was not a very mature scheme, but since then, a lot of mature and well-developed schemes have been proposed, such as BFV, CKKS, and BGV. These schemes differ in the type of data that they operate on. So, for example, BFV only operates on integers. So you can only encrypt integer values using this. So this is one of the reasons why we choose CKKS scheme for neural networks, because it can operate on real numbers, including decimals and floating point values. And as we know, neural networks also operate on floating point values. So CKKS scheme is well suited for neural networks. The second reason why CKKS scheme is well suited for neural networks is because it supports something called single instruction multiple data. So in many modern processors such as Intel processor and AMD processors, they all have support for simmed instructions, which means you will have a single instruction, suppose addition. Suppose you have two arrays and you want to add each element of the array, like first element with the first element, second element with the second element of both the arrays, and so on. Instead of reading one element at a time from both, adding them and storing them, you can use a special instruction that will at one go add all the elements and store the result. So this is something called sim. So CKKS also supports a similar property wherein you can perform, wherein a single instruction can operate on multiple encrypted data points in one go. So this is why this will help parallelize the operations and speed up the computations. So since we are going to use the CKKS scheme for our neural network, we will first take a look at how the CKKS scheme works. So first, suppose we have m data points. It can be an image, it can be a document, it can be text, whatever. We need to convert that into numbers, which is something all neural networks, modern neural networks require. They only operate on real numbers. So once we have performed a conversion into real numbers, we need to convert them into a polynomial of degree n. Now, the higher the degree of the polynomial, the more secure it is. So usually we use polynomials of degree 256, 512, 1024, multiples of 2, but also uh, order of thousand or hundreds, minimum hundreds. So then this polynomial is encrypted. So now the polynomial that you have obtained, so you have converted your m data points into a polynomial. Now you need to encrypt this polynomial using a secret key, which only the user will have access to. Now, once this polynomial is encrypted, we will again get another polynomial, which is the encrypted form of the original polynomial. We will send this encrypted form of the polynomial to the server. The server will perform all operations only on this encrypted polynomial. Now, suppose we send two polynomials. We know that each polynomial has m data points in it, whatever the m data points are. Now, if we add two polynomials, effectively we are adding m data points plus m data points in one single addition operation. This is exactly the single instruction multiple data property that we spoke about. This is also why CKKS is extremely effective. Same goes with multiplying. If we multiply two polynomials, we are effectively multiplying m into m array in one single multiplication operation. Then the resulting polynomial after the addition or the multiplication, whatever it is the cloud server is performing, whatever is the resulting polynomial, it is sent back to the user. The user will first decrypt it using the same secret key. After decrypting it, he has to decode it to get back the original, to get back the real number values. So the workflow is simple. You have real number values, you convert them into polynomials, you encrypt the polynomial, you perform operations, you decrypt the polynomial, and then you convert the polynomial back into m real number values. Now, this sounds lovely. So, why is it not being used everywhere? There are a couple of reasons why homomorphic encryption is still in research phase and has not been adopted widely in the industry. Even though it offers strong guarantees for privacy and security, it is extremely slow. So, when you perform any sort of computation on a encrypted data, it is orders of magnitude slower than performing operations on regular data. And the reason for this is simple. If you want to add five numbers, you can just add them, even if you add them one by one. But if you convert them into a polynomial of degree 1024, then you have to add two polynomials which have 1024 coefficients. So the number of operations obviously increases. So this is why performing operations on encrypted data is extremely slow. The second thing is, obviously, if you're converting to a polynomial of degree 1024 or 2048 or 4096, you're going to need much more space compared to regular data. So encrypted data not only is slower to perform operations on, it also requires much more memory space. And the third reason is that homomorphic encryption schemes, as we spoke about, most of them work only on polynomials, which is why we were converting real numbers into polynomials. So these homomorphic schemes only work on polynomials. So it becomes difficult to implement functions that are non-polynomial in nature. such as sin x and cos x. So these are non-polynomial functions. If we want to perform, suppose, sin x or cos x, we will have to use polynomial approximations such as the Taylor expansion. And obviously, if we are using approximations, the accuracy will decrease, especially if you compound these approximations. So that is the third problem. There can be a drop in accuracy. Now let us talk about our hardware accelerators. So what are hardware accelerators? So we spoke about the problem of speed. So we said that performing operations on encrypted data is extremely slow. One way to deal with this problem is to develop specialized chips. So, hardware accelerators are such specialized computing units which are designed to perform specific tasks more efficiently than general purpose CPUs. So, CPUs are very versatile and flexible. They can perform a lot of algorithms, they can perform a lot of operations, from running browsers to performing mathematical operations to watching videos, movies, etc. So they can perform their very general purpose. However, this does not mean that they are highly efficient at each algorithm. So they sacrifice efficiency for flexibility. But suppose we only want to design a chip that can perform only a few operations or a few algorithms, but those algorithms it will perform with much greater efficiency and speed. So this is the core concept of hardware accelerators. Some common examples that we all know are GPUs. So we know that GPUs are optimized for parallel workloads. So they excel in algorithms which have a lot of parallelism, such as matrix multiplication in deep learning and video rendering. So these are all operations that can be parallelized. So the GPU is a specialized chip which deals with mostly parallel algorithms. Second is TPUs. So we have special hardware accelerators for AI also now, which are just specialized for performing matrix multiplications. So they can thousands and millions of matrix multiplications per second, something a regular CPU cannot do. So these are tensor processing units. Such an example is Google's tensor processing unit. So we can design our own hardware accelerators to speed up CKKS scheme. This is the core idea. So that when we perform the encryption, decryption, and all the other algorithms, it will be much faster than performing on regular CPUs. To design hardware accelerators, we have two key options. One is FPGA boards, and second is ASICs. So, what is an FPGA board? An FPGA board is basically a reconfigurable hardware, so that can be modified repeatedly. So once you design your chip and you design all the algorithms that you want to implement on your chip, you can first test the design on an FPGA board. If it doesn't work out, or if the efficiency is not high, or if there are some issues, you can redesign the FPGA board with another algorithm or another design. So this is the advantage of FPGA boards, that they can be repeatedly changed. So it's good for prototyping and testing your initial chip design. The second technology is ASIC, so which is application specific integrated circuit. Now this is your final chip. Once it has been manufactured by semiconductor manufacturing companies. Once this chip has been manufactured, it cannot be changed. But this chip is going to be much more efficient and faster than FPGA chips also. So so basically workflow is that we first will prototype and test on an FPGA board. We will go through many iterations, and the best and efficient design will finally be manufactured into an ASIC, and this ASIC will finally go into the cloud servers or mobile phones, etc. So in that sense, TPU is also an ASIC which is implemented in most of Google's mobile phones. So we are going to be designing a CKKS accelerator specifically for convolutional neural networks using FPGA boards. We are using FPGA boards because again we can change our design multiple times, and we can tweak parameters, and we can check the efficiency and speed boost that we are getting. So in this project a specialized chip is designed to speed up CKKS scheme operations for CNNs, and it is tested using the AMD Kria KV260 SoC board. So it's a system on chip which combines an FPGA board, but it also has an ARM processor. We will talk about this split. What we are targeting here is the most compute intensive part of the convolutional neural network, which is the convolutional layer. So we know what the initial stage of any CNN is, the convolutional layer, which performs a large number of multiply accumulate operations. So there's a kernel, and the kernel will slide over the image and sliding over the image, it will result into a new matrix of smaller dimensions. So each neuron we know processes multiple overlapping regions depending on the kernel sliding window. So there's a lot of repeated computations, and the data volume can is going to be extremely large. So this is the main performance bottleneck in a CNN inference: these sliding operations, sliding over the image and multiplying and adding, multiplying and adding. And especially when your data is encrypted, the performance bottleneck will be even higher. So we are trying to speed up this specific operation, which is the convolutional layer. So this is a simple example of a convolutional layer. This is your input image. This is your kernel, and the kernel will slide over the input image and create a new matrix of smaller dimension. This is your standard CNN convolutional layer. This is not dependent on any encryption scheme or whatever. So, but now suppose we have encrypted data. So, how can we perform convolution on encrypted data? If you take a look, right now, standard CNNs perform convolution on matrix form of data. So, you can see there's a matrix, and the kernel is also a matrix. So, it is much simpler to perform convolution. We just need to slide the kernel. However, we have discussed that in CKKS, we do not have any matrix or real numbers. We have polynomials. So your input image will be one polynomial and your kernel will be your second polynomial. Now, how will we perform convolution? How will we slide the kernel across the input, etc.? How will we do that in the CKKS scheme? So in the CKK scheme, we need to use something called slot rotation. So you have your input image, which is a polynomial, and you have your kernel. Now we need to slide the kernel and multiply it, then again slide it, again multiply, again slide, again multiply, till we obtain our final matrix or final polynomial. To do this, what we do is we rotate the input image to align it with the kernel. So first of all, each kernel weight is stored as a plain text polynomial. So the kernel itself is a polynomial, as we have discussed. The encrypted image is rotated to align the slots with the kernel window. So again, if we go back to this example, right now we can see that the first 3 by 3 square is aligned with the kernel. Then the next 3 by 3 square will be aligned with the kernel if we slide by 1. Then again, if we slide by 1, the next 3 by 3 will be aligned. So the similar alignment needs to be done on the polynomial. And to do this, we use something called the automorphism property of the polynomials. So, but the core concept remains the same. We take the polynomial, first we multiply it with the kernel, store the result. Then we align the polynomial by rotating it, multiply with the kernel, store the result. Then again we align the polynomial by rotating it, multiply with the kernel polynomial, store the result, and we do this how many ever times required. So each rotation, we have a ciphertext and a plaintext multiplication. Your kernel weights are not encrypted. Only the user data is encrypted. So the user data is ciphertext and the kernel is plaintext. So the plain text and ciphertext are multiplied, then the ciphertext is rotated, then again multiplied, then again rotated. So basically what this boils down to is polynomial multiplication, then polynomial addition, polynomial multiplication, polynomial addition. In between them, it's polynomial rotation. So here is the actual mathematics and architecture overview of our chip for convolutional unit. So you have your ciphertext even coefficients. So whatever the user has, whichever polynomial the user has given to the server after encryption, all the even index coefficients like 0, 2, 4 will be stored in one part of the memory. All the odd index coefficients will be stored in another part of the memory. This is because we can exploit the parallelism. We can operate on the even coefficient separately and the odd coefficient separately. So we are reducing the time to process one polynomial by half. The first part is that they go through an automorphism unit. This is responsible for rotating the polynomials to align it with the kernel. After we have rotated the polynomials, we have to perform something called the key switching operation. The key switching operation ensures that the rotated polynomial is still valid under the original secret key. So we talked about the user encrypting the data using his secret key. But now if we rotate the encrypted data, the original secret key is no longer valid. So the user will not be able to decrypt the data using his own key. To make sure that the user is still able to decrypt data using the original key, we have to perform something called the key switching algorithm. I will not go into the math of that, but this is the need for key switching algorithm. It ensures that the rotated polynomial is still valid under the original key. After we have done the key switching, we will do plain text multiplication, a plain text being the kernel. So after we have rotated and performed key switching, we can multiply the encrypted data which is the image, with the plain text polynomial, which is the kernel. And after that, we can add them up and store the result into another two memory, even and odd. So this is the overall architecture of the convolutional unit. The other important thing to note is that this design is pipelined. So processors and most of the processors are pipelined. So suppose you have multiple polynomials coming in. So it is possible that the first polynomial is in this stage, and the second polynomial is in this stage, and the third polynomial is in this stage. So typically, if you don't pipeline the design, what will happen is that the first polynomial will go here, then it will go here, then it will go here in the third stage, then in the fourth stage, and only then can a new polynomial enter it. So total four operations have to finish before another polynomial can enter and be processed. But if you pipeline the design, what will happen is that the first polynomial will enter here. Then when the first polynomial moves to the second stage, another polynomial will enter into the first stage. Then when the first polynomial moves into the third stage, this polynomial which was in the first stage will move to the second stage, and a new polynomial will enter the first stage. So this way we can see that the polynomials are going through a pipeline instead of waiting for the entire operation to finish. So this will also speed up your final result. Now there is another problem here. We spoke about the convolution basically being polynomial multiplication and then polynomial addition. So polynomial addition is extremely efficient. It's just adding. So we do not need a lot of resources to do polynomial addition. However, polynomial multiplication is expensive. It has a time complexity of O of n square, obviously, because you have n coefficients in the first polynomial, n coefficients in the second polynomial, and you have to multiply these two one by one. So you have a time complexity of O(n) square. Now, since we are using extremely large polynomials, degree 4096, etc., this becomes extremely slow. To solve this, we use another mathematical trick called number theoretic transform. So number theoretic transform or entity is similar to the FFT algorithm. It will take your polynomial and convert it into another domain. Now, if you want to multiply two polynomials, you will convert it into the entity domain, then do coefficient wise multiplication. So you just need to multiply 0th coefficient with the 0th coefficient of the second polynomial, first coefficient with the first coefficient of the second polynomial, third coefficient with the third coefficient of the second polynomial, and so on. And then you get the resulting polynomial and you perform inverse number theoretic transform and you will get back the result. Now if you analyze the time complexity of this whole process, it comes out to be O of log n, n into log n, which is much more efficient than n square. So we have also included two deeply pipelined entity engines. Again, these are pipelined, which means you do not have to wait for the entire polynomial to finish multiplication. The first polynomial can enter into next stage and another polynomial can come into the first stage and so on. So these design is also pipelined entity engines, and we have two entity engines, which means two polynomials can be converted into the entity domain at the same time. So these are two parallel entity engines. One polynomial will go into the first engine, second polynomial will go to the second engine. The result will be multiplied. And then there are two identity engines, which is inverse entity engines. They will, again, the first polynomial, the result will go into either of the two inverse entity engines. So this is the design of a single entity engine. It will read memory from one of the BRAMs. Again, we are maintaining even and odd coefficient, even index and odd index coefficient split throughout the design. This will help. This basically helps speed up the processing. So first we'll read one even index and one odd index. The butterfly unit, which is the core of the number theoretical number entity math. We will not go into the math in this presentation, but there are two butterfly units per entity engine. So at one time, basically, we can process four coefficients of a polynomial because of two butterfly engines. So the first one will take two, the second one will take two, it will process it. So at a time, we can process four coefficients of a polynomial. And like this, we have two entity engines. Now there is another problem, which is the reduction operations. So now in CKKS, when we have the polynomial coefficients cannot grow to an arbitrary size. They cannot go to 1 million, 2 billion, 3 billion. All of the polynomials are bounded by something called the ciphertext modulus q. What is the ciphertext modulus q means? It basically means that none of the coefficients can exceed the value of q. If the coefficient suppose you multiply two polynomials and the coefficient is becoming bigger than q, then you have to take mod q, and the remainder will become the new coefficient. Simple example is if 3 is your mod q, and your multiplication result is 6, then you have to take 6 mod 3, which is equal to 3. So this is the which is equal to 0. So 6 mod 3, which is equal to 0. So that will become your new coefficient. So that is the concept of ciphertext modulus. How this helps keep the coefficient size smaller. If you don't have this modulus, then if you multiply many times, your coefficient size can become a million, billion, trillion. So the sizes will become too big. So that's why we keep a modulus q. However, the problem is that performing this modulus operation in hardware is not efficient. It is slow compared to simple addition and multiplication and left shift and right shift. So we would like an algorithm which can somehow let convert this mod operation into a series of addition and multiplication. So one of such algorithm is the Barrett reduction algorithm. So this replaces the division or the remainder operation with the series of multiplication and bit shifts. So this makes it more hardware friendly. So that's why we have implemented Barrett reduction for all our modular reduction operations. You can see a simple pseudocode of this operation. I will not explain it in this presentation, but here it's a very simple operation. So it basically converts your modulus into a bunch of bit shifts and multiplication. So you can see one multiplication is here. Uh, so that is the idea behind, and this is your this division is basically a division with two, so it can be implemented with a simple left shift operation. So that is the idea behind barrel reduction. So these are your left shifts, and this is a simple multiplication. So we can. The idea is basically that we have reduced inefficient modular reduction mod operation with more efficient bit shifts and multiplication operations. So now we will talk briefly about the implementation of this entire design. So this design was again, like we mentioned, implemented on the KV260 Vision AI Starter Kit. So this board is specialized for CNN networks, the traditional CNN networks, which is why we have modified it slightly to be compatible with CKKS data. So this includes a processing system. So this includes a processing system which is an ARM processor with 4 cores, and it also has an FPGA fabric. So this entire board is composed of two main parts. One is your ARM processor, and the other one is your FPGA fabric. Now the advantage of this is that some operations we can perform on our regular CPU, which is the ARM processor, and only the operations of the CKKS scheme we will mitig- uh, we will transfer to the FPGA. So the responsibility of the CKKS encryption, decryption, multiplication, rotations, all those, the responsibility of that will be on the FPGA side, and the CPU will handle receiving data from the user, sending data back to the user, all the connectivity part, so that the CPU will handle efficiently. So this is the advantage of using a system on chip. It includes both. If we only had the FPGA, then it would become another challenging task to implement networking on the FPGA side. So the heterogeneous setup allows tight integration between software control and high performance encrypted computation. So we can use the software to control the entire process, such as when to receive the client data, when to start the operations, how to send the data back to the client. So all this can be handled on the software side, which is the ARM processor, and the speed up and all the computation intensive parts such as encryption, decryption, and multiplication, polynomial rotations, all the parts which require a lot of time and memory, that will be handled by the FPGA part. What is the design flow? So to design this entire hardware, we have used the Vitis RTL kernel flow. So Vitis is another software. It's like an it's a hardware development kit offered by AMD, who makes these FPGA boards and SoC boards. So the complete design was synthesized in a Vivado 2025. So Vivado is again a software which helps you synthesize your design. So you write down your Verilog code and your system Verilog code, whatever code you're writing down, it will finally be synthesized by the Vivado into a bit stream, and the bit stream you can upload to your SoC, and it will run the algorithm or the design. Which is why, again, like we mentioned, FPGA you can always change, because you can always change your bit stream and you can keep uploading a new bit stream to your FPGA, and again you can change the design, generate a new bit stream, and again upload that to your FPGA. So this is the advantage of using an FPGA. You can prototype and experiment with a lot of different designs. Now, the second, one of the more important points is that since we have a processor which we are using for ARM processor, which we are using for control, such as when to receive client data, when to send client data, we need to make sure there is synchronization and communication between the FPGA and the ARM processor. So the FPGA is performing all the computations in polynomial rotations, multiplication, modular operations, etc. So there needs to be a communication, such as the CPU should be able to tell the FPGA start operations now. FPGA should be able to tell CPU that I am done with the operations. You can send the result to client, etc., etc. So this communication must be there between these two layers. This is implemented using the AXI protocol. So the AXI protocol is a communication protocol, and the way it works is simple. There's something called AXI control protocol. So first, the controller is the host. It will first read the data from the client. So the client has encrypted the data on his phone and sent it to the server for process for neural network processing. So the server will receive the encrypted data. It will write it to a region of memory. It has written that encrypted data, stored it in some region of the RAM memory. Now it will tell the FPGA board or the FPGA fabric that I have received the data. You should start processing it. And here is the address where the data is stored. So it will do this using the AXI Lite protocol. So the AXI Lite protocol will do this. Then the FPGA board will read this signal, the signal for starting the operations and also the memory address. Then it will use the AXI 4 memory mapped protocol to read from the address that the CPU has given to it. So the CPU will give the address, and then the FPGA board will read from that address, and it can start performing operations. So this is the main concept of communication. Once the operations are finished, again the FPGA board will write the results into another region of memory, or maybe the same region of memory. It will overwrite the data. It will tell the CPU that I have completed my operations using AXI 4 Lite protocol, and it will also send the address where it has written the results. So the CPU, once it receives this complete signal that the operations are complete, it can read from the memory where the FPGA board has written the final result and then send it back to the client. Now, again, as discussed, once the client gets this result, it can decrypt it and get the analysis or prediction result. So this is the final design that was synthesized by the Vivado. So I will show you the code in a moment and explain the main aspects. But this is how the final design looks. So this is your entire convolutional unit. So the first thing is your kernel core axi. So this is the topmost level module, top level function. You can consider this the top level function, like the main function in C++. It will call a kernel main function, and the kernel main function will call the convolution function. So inside the convolution function, you have a convolutional unit, which is performing the actual convolution that we discussed: polynomial rotation, polynomial multiplication, polynomial addition. Side by side, we have two entity units. So entity units are the ones responsible for taking a polynomial and converting it into the entity domain, so that it is much more efficient to perform the multiplication. Inside the entity unit, you can see butterfly unit 1 and butterfly unit 2, as we discussed. Each entity engine has two butterfly units. So these are the two butterfly units. Similarly, the second engine also has two butterfly units. Inside the convolutional unit, you can see two key switching engines. Keys, KS stands for key switch, and this stands for three key switch engines. So we can perform three key switching operations at the same time. And it also has automorphism engines inside, as we discussed in the initial pipeline, which you can see here. So these are all part of the uh, convolutional unit. So there's a key switch, three key switches, and three automorphism units, and four multiplication units. So similarly, you can see this here. There are three key switching units: KS1, KS2, KS3, three automorphism units, and four polynomial multiplication units. So this is the overall design of the architecture, as you can see here. Let us take a quick look at the results. So as we discussed, we have implemented this on the Kriya platform, KV260. And these are certain resource usages. So each FPGA board has a certain limited amount of resources. The block RAM is the memory. So there's only 144 block RAM units, and we have used 80 of them. Mostly these are used for storing constants and certain pre-computed constants, which will help speed up the operations. So that's why we have pre-calculated those constants and stored them. We have LUTs and registers. So registers are basically locations where you can temporarily store memory. It's also there in CPU, our regular Intel CPUs. So registers are where you store the uh, temporarily store the memory. And LUTs are used to implement operations such as AND operation or operation, any bit shift right on a hardware level. So LUTs are the ones. So you can see the resource usage. Next, let's talk about the speed up. So if we compare a CNN that is running on the CPU and it receives encrypted data and it has to perform convolution on the encrypted data, compared to that, our hardware design achieves a speed up of 25 times. So if the CPU takes 10 seconds to perform convolution on the user encrypted user data, if the CNN network that is running on a Intel processor or a AMD processor, any other processor, if the CNN network is running on that, it will be 25 times slower than the CNN which is running on our hardware. But if we include the time it takes to receive data from the user and then transfer it to the FPGA, even then we have a 2x speed up compared to the CPU design. So then we can conclude that mapping polynomial arithmetic onto FPGA significantly improves the performance of the system. What are the future work that we would like to do? So right now we support only convolutional layer of the CNN. So the CNN can only perform convolution, but we know that the CNN also includes fully connected layers, and it also includes activation functions. uh, one of the future goals is to implement these also on our hardware. Right now, we only targeted convolutional networks, convolutional layer, because they are the slowest and the most compute intensive. Uh, and the other problem is that, like we discussed, some of the activation functions are not linear. So ReLU and sigmoid, sigmoid depends on e to the power minus x, and ReLU is also not a linear function. So it's hard to approximate them into using polynomials. It will decrease the accuracy. So there is some research work going on how to approximate these activation functions as polynomials, so that we can implement CKK scheme or any other homomorphic scheme on them. The second is ciphertext multiplication. For example, I mentioned that the kernel weights are not encrypted, they are plain text. However, this introduces another security flaw, which is if the attacker gains access to the cloud, he can retrieve the weights of the model. So he can get to know all the weights of the model, and so he can copy the model and implement it on his own server. So this is one a common AI attack wherein you try to estimate all the parameters of the AI model. So to prevent that, one technique would be to encrypt the weights also, all the kernel weights, all the fully connected layer weights, all the bias. So if you encrypt all of that, then even if the user has access to the server, neither can he get user data, because user data is already encrypted in our hardware. And if you encrypt the weights also, he will not be able to get any of the model weights also, so he will not be able to copy the model. But to implement this, we will have to implement ciphertext multiplication, which becomes much more complex in any homomorphic encryption scheme. So the idea here is that if you have a homomorphic encryption scheme, any scheme, it's easy to multiply a plain text, which is non-encrypted polynomial, with encrypted polynomial. That's a standard one-to-one multiplication. It's also easy to multiply two unencrypted polynomials, again normal polynomial multiplication. But if you have two encrypted polynomials, two ciphertext, multiplying them is much harder, and it might also not give the correct result. Sometimes it might also lead to wrong results. So there's research going on how to perform ciphertext multiplication also. So at the time, we keep the model weights and the kernel weights unencrypted. So this is the references for the presentation. Now let us take a quick look at all the important parts of the code. So the entire code is written in System Verilog, which is a hardware description language. It is used to design hardware. This is different from programming languages like C, C++. So here is the code for entity. So in hardware description language, we split each functionality into small submodules. So we don't want to implement a big function, because if there is any error and we implement it, it is hard to change it, especially if you're designing ASICs. So this, for entity, we have a lot of modules. One is responsible for just generating addresses of how to read the polynomials, which index to read. Should I read the first index, second index? So one module is for address generation. The second module is Barrett reduction, which is the algorithm we spoke about. It's a simple algorithm. This performs reduction of the coefficient. So you can give it a coefficient and ask it to reduce it, like modular operation. So it will perform modular operations. This is implementing memory semantics. So this is basically implementing a BRAM. So in FPGA, you don't have given, you have to program the BRAM also, which is the RAM storing memory. That also needs to be programmed using hardware description language. Then we have the butterfly unit. Now the butterfly unit is the most complicated, one of the more complicated modules, and it's a little bit lengthy also, because this is the one responsible for actually performing the entity operations. So if you look at FFT algorithm or entity algorithm, you will come across butterfly units. So this basically implements the butterfly units, and internally it calls all of these mod multiplication, mod addition, mod subtraction modules, which we have defined as well. So here is mod multiplication. It just performs a multiplication, then it will call Barrett reduction. So it will perform a multiplication A into B, then it will do mod Q. And it will do mod Q using Barrett reduction, not the standard mod. Same with mod subtraction. It's a simple subtraction. And then after performing the subtraction, it will make sure that the result lies between 0 to Q. So if it has gone negative, you have to add a number to make sure it lies between the 0 to Q range. And similarly the same thing goes for modular addition. So you can see that we are just taking sum, we are adding a plus b, then we are shifting it into a register, and this is again Verilog semantics. This is the temporary register here. Then once we have shifted this to a register, we must reduce it by subtracting it with the mod value. So again, the point here is that if you add two numbers and it becomes more than q, so if you add, like, if your q is 6 and you're adding 2 and 2 and 4, or 2 and 5, so 2 and 5 is 7, which is more than 6, so you have to subtract 6 to get the modular form, which is 1. So these are the different modules that are implemented for entity. Similarly, we have different modules for automorphism, which is the which automorphism is the algorithm that rotates the polynomial and aligns it with the kernel. So this is the algorithm for automorphism. Again, everything is written in Verilog. Uh, this is the top level unit, convolutional unit, which integrates all the units: automorphism, key switching, polynomial multiplication. It's the design I was showing you. So this integrates all the modules, and it just reads the just makes the all the synchronizes all the modules involved. Then there is the key switching module, which we talked about. It's responsible for ensuring performing key switching, which ensures that the polynomial that we have obtained after rotation, it is still valid in the original secret key that the user has used to perform encryption. So we need to make sure that the after rotation also the user is able to decrypt the data. So this the key switching performs that operation. Then we have other smaller modules. One is ciphertext plain text multiplication. So this will just take two polynomials and then multiply them coefficient wise, and we are assuming that we have already performed entity on them. So once we have performed entity on them, if we can just take first polynomial, first coefficient of both, multiply it, store the result. Second coefficient, multiply it, store the result. Third coefficient, store the result, multiply it, store the result. So this is the module that performs that operation. Uh, so you can there are comments on most of the modules, so you can go through the code if you want to understand exactly how the code works. Although you will need knowledge of Verilog and hardware design for that. But in essence, this is the entire design. So we are the most important files are this convolutional, which performs the actual CNN convolution operation that all the CNNs have. The only and the key difference is that it does not perform it on regular data. Otherwise this will not be very complex, because on regular data it's just matrix multiplication and matrix sliding. This convolutional operation is entirely done on encrypted data, which is homomorphically encrypted data, which is why it is secure and helps protect the privacy of the person who's uploaded the data. So this is the most important module to understand. And the other important modules to understand are the entity algorithm. So this is the entity controller. This integrates all the entity parts, which is butterfly units and it is also pipeline, so there needs to be synchronization between multiple pipeline stages. So suppose if they are if first polynomial is in third stage and second polynomial is in second stage, once the third polynomial moves ahead, we need to make sure that the second polynomial also moves ahead, otherwise the pipeline will get blocked. So to deal with all those sorts of synchronization and all the issues that might arise out of it, we have this entity controller which controls the pipeline and makes sure that everything is moving one step forward. So yeah, that I would like to. One last thing is that Vivado will auto generate your communication protocol. Let's discuss this. That, like we discussed, we need to have a synchronization between the CPU and the FPGA board. That is using the AXI protocol. So all this code is not written by me. This is done by Vivado automatically. So Vivado has predefined functions for these communication protocols. Uh, yeah, so that is it for the presentation. I hope you learned something from it, and thank you so much.